I'm really excited about this lecture. I like this topic very, very much. I hope you'll like it too. So today I'm going to talk about hardness within P. Okay. So far in this course, in complexity in 455, we've pretty much gone with, we'll say P polynomial time is this sort of equated with efficient. Okay. Once we get to a problem in polynomial time, we say, hey, that's an efficient algorithm. Let's go with that. And it's a pretty reasonable definition, especially if it's not an algorithms class, hardcore algorithms class, where we're going to nail down every polynomial factor. So it's an okay kind of pair of things to equate in your mind for basic purposes. And it's certainly true for the most part that if you have an algorithm that's not in polynomial time, that's really probably not going to be efficient in any sense in practice. And it's also true that if you have like a problem, like I don't know, SAT or 3-coloring or 2-SAT, it's often the case that the big conceptual leap in algorithm design is getting it down from like kind of the trivial brute force algorithm, which is usually exponential time, try all possible solutions, down to a polynomial time algorithm. That's really where often the magic happens. But okay, in life, the reason we care about any of this stuff is because we're eventually going to program computers to do it. And in life, whether or not this is really accurate is up for debate. In fact, you don't even have to worry about algorithms running in time n to the 100. You can even ask yourself really whether like an n² time algorithm is really efficient. You know how it is these days. They're talking about the era of big data and so forth and so on. So I mean, it's really true that you should think to yourself that a problem where the input size n is a billion is shouldn't be considered a very big thing, So if you have an order n time algorithm or an n log n time algorithm, that's probably okay. Doing an algorithm that takes 10 to the 10 steps, 10 billion steps, that's okay. Well, that's not a problem. But if you have an n² time algorithm and it's taking 10 to the 18 steps, that's not okay. That's not really gonna fly unless you're going to devote like hundreds of computers and multiple years to solving the problem. So you can see it really makes a big difference. And honestly, the gold standard for actual efficiency is kind of like order n times polylog n. So in some sense, like n² is not even that awesome. I mean, it's OK if n is whatever, 1,000 or 10,000 or something. But we have to worry about that. But at the same time in this class, I mean, we were always like, oh, polynomial time, what's the difference between n, n², n³? We don't care. In fact, we didn't even care that much about the differences between our models, like 1-tape Turing machine, 2-tape Turing machines, RAM model, where there actually could be like differences in running time that were like quadratic. OK, so in this lecture, we're going to try to think more carefully about like running times within P. OK, and let me make a couple of remarks about that. One, the model now actually really matters. I mean, if you're worried about n² time versus n time or n log n time or whatever, it matters whether you're actually talking about 1-tape Turing machines or 2-tape Turing machines or even the RAM model or whatever, because these can make polynomial slowdowns. And of course, what model should we choose? We should choose like a realistic one. I mean, it's stupid to, it's fun in games and stuff to show that palindromes cannot be solved in less than quadratic time on a 1-tape Turing machine. But it doesn't really tell us anything, honestly, that interesting about real computing. So, for the purposes of this lecture and for research in this area and in algorithms, you stick with like the model being this thing called the RAM model, which we didn't define precisely, but it's basically the model that you write pseudocode in. The property that you can do an operation, basic operations on, let's say, numbers that are between 1 and poly n in constantly many steps, or in one step, and you can have random access to memory and stuff. Okay, so that's a realistic model, and that's the one that we'll work in, because it's the one we actually care about. Okay, so in an algorithms class, of course, you're going to be working hard to take your favorite problem and maybe first solve it in n² time, then maybe try to get a better algorithm that solves it in n log n time or something. But this is a complexity class, right? We're into negative results. So we have to ask ourselves, could we even have any techniques for showing that a problem cannot be solved faster than n² time? we've talked about, showing problems cannot be solved in polynomial time. We can't do that either, but if you assume p does not equal np, then you can do it for lots of problems. So what are we going to do? So for example, let me just give an example. Like back in lecture 10 or something, we talked about problems that are in P. And we saw, just as this was one example of a million problems that are in P, we solved this longest common subsequence problem. Okay, where you're given two strings, you want to find the longest string that appears in both of them, not necessarily consecutively, but in the correct order. And this is an important problem for text processing and computational biology and so forth. And we saw that it could be solved in time n squared using a very basic algorithmic tool, dynamic programming. And that's basically the fastest known algorithm. I think maybe they can get like n squared over some logarithmic factors, but it's basically the fastest known algorithm. And we're interested in trying to understand, could we possibly show something like not in time order n to the 1.99? Then at least, we could maybe try to stop searching for better algorithms. I mean, we'd be kind of sad because n squared is not so fast, but if it's the best you can do, then it's the best you can do. Now, we don't have so many tools for trying to prove statements like that. Actually, we're not completely hamstrung. We have some tools. Well, we have one tool that's of a similar flavor. We have this time hierarchy theorem. Which, for example, tells us that there exists a language L such that L can be solved in quadratic time, for example, but L cannot be solved in time n to the 1.99. Okay, this is fine as long as this thing is a little bit less than this over log of this, which it is. And they have to be time constructible, but they are. But that's not great because it's more like there exists some weird language, right? This is some pretty unnatural language. And it's good to know this fact, but again, in life, we care about the problems that we care about, like longest common subsequence or whatever. I mean, not some contrived problem. Yep?
With the time hierarchy theorem that we learned in the lecture, isn't it not as strong as this? It's over a factor of log n, or?
Yeah, but this is smaller than this by more than a factor of log n. So n to the 1.9 is still much, much less than n squared over log n. Yeah, because if you put the log n to this side and that n to this side, you have log n much less than n to the 0.01. And any power grows faster than any log. So, OK, well, let's get back to here. And we kind of talked about this situation last time, where we want to prove things, and we can't prove things. So we make an assumption to try to help us. And the ultimate dream is always something like, let's try to base it on p does not equal np. Because this is the one assumption in complexity theory that pretty much everybody is willing to make. You can't really do anything without it. So this would be a great result. You could show that p not being np implies that the longest common subsequence problem, for example, or some other problem of this flavor, can't be solved in time n to the 0.99. But we don't know how to do this. And it seems kind of tough because really, it could be that np, everything in np, let's see. Yeah, I don't know. I mean, it's somehow, this is not very sensitive to the difference between n squared and n cubed and, I don't know, n to the 1.5, right? I mean, this is any polynomial in the running time. This is any polynomial in the running time. So I don't know. Anyway, we don't know how to do anything like this. So, remember last time we said, OK, in the absence of, the dream coming true, you could have a backup dream of, well, maybe trying to make one more limited plausible assumption and trying to derive many consequences of it. I mean, once you decide you're going to start making conjectures or assumptions, you could always just say, well, this is my assumption, or the longest common subsequence problem, or whatever is not in time n to the 1.99. But it's OK if that was the only thing you did, maybe. But like, I mean, you cannot just for every, there's thousands of algorithms problems. You cannot just make an assumption about every one that you care about. You want to make like 1 or 2 assumptions and derive many, many consequences from it. So let me write that. Make 1 or 2 fixed assumptions. OK, and derive from it many, dozens or hundreds, hardness consequences. And really, in some sense, the dream of basing everything off p does not equal np is really, it's like the 1970s version of the backup dream. I mean, they tried to just prove directly that problems could not be solved in a certain amount of time, and they failed. So they're like, OK, fine, we'll make one assumption. This was in the 70s, that SAT is not NP. OK, they understood that this is the same as p does not equal NP. And then, there's the whole theory of NP completeness, where you can show now like thousands and thousands of problems are also not NP. So K-clique and like, whatever, 3-color ability. And OK, there's literally thousands of problems that you can conclude are not NP just based on one assumption. OK, so that's pretty satisfactory. So in some sense, this lecture is about trying to do the same thing to derive consequences about hardness within P. And I'll just tell you how it's going. It's a very active topic in complexity theory, like today, like these days. Like, CMU was interviewing people for faculty positions, and one of the people came by as like a guy who's a leader in this area, and like this is what he's working on right now. So this is some stuff for the 2010s. So one assumption that you can make, which is mentioned a few times in this class, is called strong exponential time hypothesis. Strong exponential time hypothesis. And I'll remind you of its exact statement later. But it's sort of similar to saying that SAT requires not just super polynomial time, but like at least around 2 to the n time. OK, this is not very precise. I'll remind you of the precise statement later. But you can kind of think of it for just this moment as saying that to solve SAT really requires 2 to the n time, basically. And what we've understood in the 2000s and 10s is that if you assume this, you can actually, this looks like a kind of abstract assumption. It's about like running times that are exponential. But you can derive like very concrete and interesting results about problems not being solvable in fixed amounts of polynomial time. For example, it's known that if you assume this, then the longest common subsequence problem is not in time n to the 1.99. Or it's not in n to the 2 minus epsilon for all epsilon. So that's pretty awesome. Because they don't look obviously related. OK, so it's like fair. It's not like you cheated by making an assumption about LCS itself. And that's pretty interesting. So this is a very strong assumption, much stronger than p does not equal np. And like not everybody necessarily believes it. Even like some complexity theorists don't believe it. I kind of believe it, but I got no particular reason to believe it. But anyway, if you believe it, it implies you can stop looking for like an LCS algorithm that's faster than n squared, which is a pretty interesting thing to know. Or you can look at it a different way. You can say, well, if you want to become the most famous theoretical computer science in the world by finding a SAT algorithm that's faster than 2 to the n, all you have to do is find a longest common subsequence algorithm that runs in time n to the 1.99. That looks like a lot more related to stuff that you could be used to. So yeah, there's like maybe like some nice dozen or more, I don't know, dozens of problems that also you can show to be hard within P, assuming this set. So I'll just write a few random ones. This is by no means exhausted, but like the edit distance problem, computing the edit distance of 2 strings, that requires about n squared time, which is sad for practical purposes if you believe Seth. What else we got? Oh, we'll talk about this one. Computing the diameter of a graph. requires around m times n time, number of edges times number of vertices. If you believe Seth, lots of other problems, computing like the Frechet distance between curves, whatever that is. Takes n squared time. There's some important problem called the orthogonal vectors problem that takes about n squared time. Okay, so there's lots of, I mean, this is all from this decade, lots of interesting problems where we know that, there's no faster algorithm better than, in most cases, like a relatively simple algorithm, usually some kind of dynamic programming algorithm, if you believe that SAT really requires 2 to the n time. That's pretty cool. Now, this one conjecture, Seth, strong exponential time hypothesis, has not solved all our problems. And the picture is not quite as clean as it is for p does not equal np, but it's a current topic of research, not one from 40 years ago, so that's to be expected. And in fact, pictures like this were actually being drawn a lot earlier. So in '95, there was like a subsequently influential paper by these two people, Gauchentan and Overmars. And they considered a problem in algorithms, which is kind of famous, kind of infamous, called threesome. And I'll tell you what it is, because it's an interesting problem. It's cute. Threesome is you're given an array of integers, n integers. And here's the task. You just want to determine whether there exists 3 positions I, j, and k such that ai plus aj plus ak equals 0. It's possible, right? They can be positive or negative. That's it. That's the whole problem. Now, it's definitely in polynomial time. It's actually clearly in n cubed time, because you can just try all possibilities for I, j, and k. And it's a fun, if you've never seen this problem before, it's a fun exercise for you to try to get an algorithm that runs in time about n squared. It's not too hard to get something like n squared log n or something. And that's the fastest algorithm that's about the fastest algorithm that's known for the problem. You can get a little bit better, but like n squared over log factors. But that stumped people for a long time. And people, in particular these people, considered, like, what if we just assume that this problem really requires n squared time, that there's no faster algorithm? So I mean, this is like a case where they just took the problem that they cared about and just made an assumption about it. But it's not stupid, because they show that it implies hardness results, similar hardness results for lots of other not as obviously related looking problems, especially in the field of computational geometry. So again, I could draw like a dozen consequences of this assumption. I'll just write like 3 random ones that I picked out. Checking for if 3 points are collinear requires about n squared time. So this is a problem. You're given a bunch of points in the plane, and you want to know, are there 3 of them that are on a line? You can do that in n squared time. And this shows that you cannot do it faster if you assume this. And that's like a basic computational geometry task that you'd want to actually be able to do like kind of efficiently. OK, like here's another one that just like I was looking at the list and it caught my fancy, like hole in union of triangles. So in this computational geometry problem, the input is a list of n triangles in the plane. And you want to know if you like take their union, you'll get like kind of a triangular blob. And you want to know, is it like simply connected, or is there a hole in it? It's a cute problem, and you can do it in quadratic time, and you can't do it any better if you assume this conjecture about this threesome problem. Or another one that people like to quote is like robot motion planning in the plane. It's a bit of a fancy name. This problem, whatever it is, it also requires n squared time. Well, I'll tell you what it is. You have like a plane, and you have a robot, which is a line segment. And you have barriers, which are also line segments. And you want to know if you can get the robot from like a start to a finish past all the barriers. And like the robot can rotate and translate. It's the whole problem. It's like, I don't know, programming your Roomba or whatever. N squared time. So this is like another example of, this backup dream kind of being realized. You make one concrete assumption, which, OK, it's an assumption. But then you get many consequences. Okay, so there's like, there's like a whole 50-page paper about other problems that are hard, assuming threesome is hard. Let me tell you or draw you another picture that looks like this. You might start to wonder that, like I'm going to show you another problem, assume that it's requires some running time, and show you a bunch of other problems that are you can conclude are hard. You might worry that's kind of spiraling a little bit out of control with too many assumptions, and well, there's only going to be 4 pictures like this. It's true, though. I mean, it's a little unwieldy, but well, as I said, it's current research. Things are in flux. So hopefully we'll maybe get an even more gloriously unified picture later. Anyway, though, let me tell you about another basic problem. This is APSP. That stands for all pairs shortest paths. OK, so this is a pretty well-known problem, basic graph problem. You're given a graph, undirected graph. You want to know the shortest path between all pairs of vertices. So I mean, there's like n squared pairs of vertices. So it's like n squared data that you need to compute. And the fastest known algorithms for solving this all take about n cubed time. OK, there's a pretty well-known algorithm from like a billion years ago called Floyd-Warshall, which the pseudocode is just like 3 for loops from goes from 1 to n. And it computes all the shortest paths between pairs of vertices. OK, and that's the fastest algorithm known for the all pairs shortest paths problem. So you can just assume it. And if you assume that this is the fastest algorithm, again, there's 5 or 10 consequences known. So for example, computing the graph radius also takes at least n cubed time. What is the graph radius? It's like the easiest way to think about it is you want to find the vertex such that if you call that vertex like the center, like every other vertex is close to it. I didn't say that well. You want to find the vertex which like minimizes the maximum distance among all other vertices to that central vertex. Somehow the most central vertex. So it takes like n cubed time. Here's another one. This is related to like shortest paths in graphs with negative edge lengths. It's called the negative triangle problem. So in this problem, you're given a graph, and there are integer edge weights, integers written on the edges. And you just want to know, is there a triangle, like a 3-cycle, where if you add up the edge weights, you get a negative number? Okay, you can obviously solve that in n cubed time. Just like try all triples of vertices and compute the edge weights, if they exist, around them and add them up and see if it's negative. And there's no better algorithm than that if you assume that all pairs shortest paths requires n cubed time. OK, so this is kind of like a, there's 4 or 5 more related problems that require n cubed time if you assume this one problem requires n cubed time. So it's kind of like these are like APSP hard problems, if you will. I'll give you one more example. As I said, it's proliferating a little bit, but last example is K-clique problem. K-clique is an interesting problem. This is just you're given an undirected graph, and there's some fixed number, like 3 or 4 or 5, and you want to know, does the graph have a clique of this size? OK, so when k equals 3, for example, the 3-clique problem is you're given a graph, does it have a triangle? Well, you can solve this in n cubed time by trying out all triples of vertices. However, there's like, I don't know if you've seen this before, but there's like a very interesting fact that you can solve it in like 3-clique. I think I mentioned this in, oh yeah, I did mention this in an earlier lecture. It's in time n to the 2.3 something. And this is however much time it needs to multiply 2 matrices. So you probably saw in 251 that there's these crazy algorithms, recursive algorithms that can multiply two n by n matrices in time faster than n cubed, or like n to 2.3, some weird number. And you can use matrix multiplication as a subroutine to solve the clique problem, the k-clique problem, or the 3-clique problem. Now if you have actually the adjacency matrix of a graph, and you square it, that takes this much time. Then you get a matrix that represents, like it has a 1 in the uv entry if there's a path of length 2 from u to v. And then you just have to go through all those pairs and see if there's also an edge from u to v. And if there's an edge from u to v and a path of length 2 from u to v, then there's a triangle. Is that right? No. Yeah, no, that's right. Yeah. OK, good. So you can actually generalize that. And it's known that you can solve the k-clique problem in time n to the omega over 3 times k, where omega is whatever your best number exponent is from multiplying two n by n matrices. And that's the fastest algorithm known. And again, if you assume this, and like these results in particular are from like 2017 or something, or 2016, then like context-free grammar parsing requires n to the omega time. So like in the 1970s, like this guy Valiant like showed that you could do this problem, context-free grammar parsing, in like n to the matrix multiplication exponent time. And people are like, whoa, that's so crazy. And that could be the fastest if you believe this assumption. OK, and some other problem called RNA folding, whatever that is, requires also n to the omega time, and a bunch of other problems. OK, so I'm going to stop there. And actually, I can stop there because, I mean, these are basically, these 4 problems are kind of, for the people who are working in this field, kind of the 4 basic problems that they always try to start with. OK, so I mean, it might not be obvious to you like why one of them is any more special than the other ones. But it's true that people have been trying to solve all 4 of these problems for a long time, faster than like kind of the basic algorithm. And we don't know how to do it. And if you assume that you can't do any better, then it explains similar unsuccess for like many, many other problems. Let me just mention that like really the pioneers, OK, so for this regime, these people were the pioneers. But in the other 3 regimes, the people who are really driving this area forward right now, one guy called Ryan Williams. He's like a CMU PhD. He was here not too long ago. Virginia Vasilevska. He's also a CMU PhD. And this guy, another, OK, there's lots of people, but these are the 3 big names, I think. Amir Abood. That's her PhD student. OK, so if you actually like, look at the papers that are coming out about new hardness results for various important problems, probably one of these 3 people will be on the paper. OK, any questions so far? Yeah.
How do these hardness proofs work? Do they use reductions?
Great question. It's like, how do these hardness results work? Reductions, yeah. I'm going to show you one. I'm going to show you actually this one, and it's all about reductions. So it's exactly like NP completeness, right? Like we assume one problem is hard, like SAT, and we make a reduction from SAT to the problem we care about. And basically, if you can solve this one fast, then you can solve this one fast in contradiction to the assumption. So exactly. It's kind of funny. Like a lot of people are like saying, like, why didn't people think of this like in the 70s? Like it's not very different from P versus NP, but somehow, I don't know, they didn't. And that's why it's like cool. I mean, there are many reductions in this area that are happening now. They're mostly elementary, so like you too can like go home and try to like prove them or find them. In the 70s, it was like fun times. Like if you proved like a new problem was NP complete, then people are like, great, and you could write a research paper and so forth. And now if you prove a new problem is NP complete, nobody really cares. But now, today, if you prove a new problem requires n squared time based on the strong exponential time hypothesis, people are like, oh, great, cool, and you can write a paper and everything. So it's, it's fun. Also, I mean, I think it's almost in some ways like more relevant to practice. I mean, so actually one reason I want to put all these up is like perhaps you will face like an algorithm problem, and like you'll think of an n² time algorithm, and you'll be like, man, I wonder if this could be faster. And like it's good to know that like these are kind of like maybe the 4 canonical hardness assumptions in this area that you might be able to use to show your problem requires whatever, n² or n³ time. Right, so this whole area is sometimes called fine-grained complexity. So that's another name you'll see for it. Because, finer grained than just something is in P or not in P. And it's really, I mean, the ultimate dream in this area is like for every natural problem, like not just figure out if it's in P or not, like figure out if it is in P, like what is the fastest polynomial time algorithm like? You want to say there is an n² time algorithm, and subject to some well-known assumption, like there's no faster algorithm. OK. So right, so how do we prove such results? Well, it's by reductions. So let me I'll remind you of how it's going to work. And in fact, you kind of even saw this idea on one homework problem, homework 5, problem 1 or something. I wrote it down. So it's just when you're doing reductions, it's going to be the same idea, but you have to be a little bit more careful about both the running time and something else, the size blow-up of the instances. Okay? So let's remember how reductions work. Let's say you have some problem A, and you have some instance x, and it has size n. OK, n bits in it. And maybe this is like some kind of string problem or something. I don't know. So like x is some string or something. It doesn't have to be. And then a reduction is like some mapping to an instance of another problem. And let's say it has some running time, r of n. And in our polynomial time mapping reductions, we just hope that this was polynomial time, and that was the only thing that we cared about. But we got to care a little bit more now. So if you're reducing problem A to problem B, then you want to map this algorithm should map any instance x to an instance y over here. And we have to worry about the size, the number of bits or whatever, in y. And this is going to be typically a function of n. And this is actually typically the more important part of the reduction. How much bigger the instance y is than the instance x. When we were just caring about polynomial time, we just said, well, this runs in polynomial time, so it only has time to output an object of polynomial size. And that was good enough, but we want to care a little bit more than that. OK, and it's a reduction, so I mean, it has one property, right? X is in A if and only if y is in B. OK, this is, well, the properties of a mapping reduction. Good. So now, suppose we had a time t of n algorithm for problem B. Then that implies what time algorithm for A? OK, so suppose we have a reduction with these properties. And then we also have a time t algorithm for B. What is our running time that we can get for problem A? Yeah?
T of S of n plus R of n.
Great. Yeah. T of S of n plus R of n. Right, so how does the algorithm work? Well, it takes x. It's trying to solve if x is in A. Takes x of length n, runs this reduction. That costs the time R of n. And then it has the new instance y. And then it runs the algorithm for B on y. But that's not just t of n time, because y is bigger. The size of y is assumed to be S of n. It's actually t of S of n. And it's kind of more typical that this term is bigger than this term. Not always, but that's more typical. Because usually reductions are not that complicated. So usually actually, R and n and S and n are kind of comparable. So if t is bigger than linear as a function, then this will be bigger than this in the most typical circumstance. Good. So that's like the forward direction of algorithms. But in hardness, we usually look at the equivalent contrapositive. Contrapositive is if there's no t of s of n plus r of n time algorithm for A, it implies that there's no time t of n algorithm for B. Okay, and this is the kind of thing that we want to use, let's say, in this picture. As I said, today at the end of the lecture, I'm going to show you this result. Okay, and so we're going to assume that there's like no basically 2 to the n time algorithm for SAT, and deduce that there's no algorithm for the diameter problem. I'll also remind you what that is. That's faster than this. Okay, so like once you have assumptions like this, you can derive consequences like this by basic reductions, but you have to be a little bit more careful about the parameters of the reductions. It's like fine-grained reductions. Like you have to, a reduction after all is just an algorithm, so it pays to be careful about its running time and parameters too. Now, in this class, we talked a lot and mainly about mapping reductions, which are reductions that look like this. They map one instance of problem A to another instance of problem B, such that x is in A if and only if y is in B. And we cared about that style of reduction because, well, first of all, most reductions, or a lot of reductions, could be put in that simple framework anyway. And it also had some complexity theoretic niceness, right? Like back when we were talking about polynomial time reductions, if you had such a reduction from A to B, and you knew that B was in NP, then you could also conclude that A is in NP, which is something you can get if you have like this more liberal style of reduction that like maybe uses an algorithm for B many times. But for this business, we don't care about such complexity theoretic niceness. All right, we just really want to know yes or no. Like, is there a n to the 1.99 time algorithm for longest common subsequence? And we'll do anything we need to do in order to try to prove such a result. All of which is just to say that, like, you can imagine it's OK in this world of fine-grained complexity to imagine, what we call Turing reductions or Cook reductions, ones that can like make many calls to an algorithm for B. Right? So in fact, you might, if you're trying to make reductions like this, you might make reduction algorithms R that actually, when they're trying to decide if x is in A, they might make many instances of B and use like a supposed t of n time algorithm for B to derive a fast algorithm for A. Okay, and then that's fine. And you can make a similar conclusion, right? So if the overall running time of such a reduction is R of n, then t of n time algorithm for B implies, R of n always plus just the sum over I of t of, let's say this has size s1 of n, size s2 of n, and so forth, t of si of n, time algorithm for A. Yeah?
Can you do the reduction however many times as well?
I'm assuming this is like the overall time.
Okay.
So I didn't write it very clearly, but I'm imagining a reduction algorithm that maybe there's like 3 calls to B, or so, like not calls to B, calls to an algorithm for B. So an algorithm that overall runs on time R of n, and from X it produces 3 instances of B, uses a B algorithm to determine whether these instances are in B or not, and combines the answers somehow to get an answer here. So in fact, the algorithm, the reduction I'm going to show you in this class is not of this more complicated form. It's just going to be a mapping reduction. But some of these reductions, Not very many of them, actually, come to think of it. But like sometimes you do use this ability to make multiple instances of the B problem, mainly in this world. So I just want to tell you that this is something you're free to do if you're trying to prove results of this nature. Any questions? OK. So I'm going to talk about this reduction. And I think probably this out of the 4 pictures, well, this one's pretty nice, too. But this is like kind of the nicest one. Like it's kind of cute because its assumption is about SAT, which is very well studied. It's not about like something running in time n squared or n cubed. And kind of maybe like these problems are like the most familiar out of all the problems where we have a consequence. And somehow the reductions I also find are like kind of nicest in this world. So I want to show you some stuff about that. So let me just remind you, what is this strong exponential time hypothesis? Remember, the exponential time hypothesis is just that 3-SAT requires time 2 to the epsilon n for some positive epsilon. It requires like some exponential running time. Strong exponential time hypothesis is kind of like if you don't have like a bound like 3 in 3-SAT, and then you can have clauses of really big size, then the running time tends towards like full exponential time, 2 to the n. So officially it's this. For all epsilon greater than 0, there exists a k such that k-SAT is not in time 2 to the 1 minus epsilon times n. OK, so like, in other words, there's some big enough k such that k-SAT is not in time 2 to the 0.9999 times n. And if you want more 9s, you can get them as long as you're willing to make k bigger. For some reason that it's not very clear, people in this area prefer to work with a very related conjecture called CNF-SAT, which is known to be implied by this conjecture. So I'll just tell you that fact. This is a fact due to Pagliazzo, Paturi, and Zane from 2001. And this one, it's kind of similar looking. It just says that if you have SAT for the CNF-SAT problem, so this is again where you have like ors of ands, ors of clauses, but they don't all have to be of length at most k. But with m clauses and n variables, 2 to the 1 minus epsilon n times poly m time is required. OK, and this is for all epsilon greater than 0. OK, so it's a bit annoying because there's 2 parameters, m and the number of clauses, and n the number of variables. But you just have to kind of learn to deal with it. Just like when you're doing graph algorithms, there's usually like the number of edges is an important parameter, and the number of vertices is an important parameter. But if it's confusing, you can mainly just think about n, the number of variables, being the main parameter, and just imagine that the number of clauses is polynomial in n. OK, so this is a conjecture. It's basically saying that SAT, even in like the CNF-SAT form, requires practically 2 to the n time. That's much stronger than p does not equal np, but that's the conjecture. And we'll see how this kind of abstract, abstruse-looking conjecture tells us something about very concrete algorithmic questions. OK, so which concrete algorithmic question? I'm going to talk about this problem now, the diameter problem. OK, so we'll come all the way down to the world of diameter. I'm going to present it not as a decision problem, but as a function problem, because it's more natural that way. That's a simple problem. You're given an undirected graph, G, and you want to compute its diameter. I'll say what that is. n vertices, m edges. And this is just the max overall pairs of vertices of the distance between u and p. Okay, so it's an undirected graph. For every pair of vertices, there's a shortest path between them. That's called their distance. You want to know what is the maximum distance that you can have in this graph. Okay, so it's a very natural problem. Simple problem. And as I state right here, well, as I allude to right here, there's an algorithm for it that runs in time about m times n, where this about means maybe don't worry about logarithmic factors too much, like log n factors. Does anybody that has a little algorithms background want to say, can suggest such an algorithm? Mm-hmm.
BFS overall is 2 BFS is over 10, and you do.
Yeah, that's right. So what? That's right. Yeah. So one simpler question, that's like a warm-up, is like, what if I just give you one vertex and I want you to compute the distance to all the other vertices? Well, you can do that with breadth first search. And in fact, if it's an unweighted graph, you can just use breadth first search. Even if it's like a weighted graph where there are actual distances, you can use Dijkstra's algorithm, which runs in time basically order m. So I guess actually, but OK, I said it was unweighted. It doesn't have to be. But if it is unweighted, you can just use breadth first search and stuff, which runs in time, I guess, order m plus n. OK? There's always this ridiculous aspect where like the number of edges could be like less than the number of vertices. Those are like really stupid graphs where like they're not even connected. So I guess I'll remember that you have to put order m plus n because maybe m, for some stupid reason, is much less than n. But basically, it's order m, the number of edges. And so that will tell you for a fixed vertex, any fixed, let's say u, you can get the distance from u to v for all other v. And then you can just do this for all vertices. Right, so actually, once you finish this, you know the distance to all the other vertices. You can pick out the largest distance among those and say, OK, this is the longest distance from u. And then you can just do that for all the u's. And like remember the largest distance you ever saw from any u to any v. Yep?
Maybe I'm being pedantic, but in the case where the number of edges is less than the number of vertices, what is the diameter?
Yeah, so I mean, it can be infinity. If the graph is not connected, then the diameter is infinity. So in fact, basically, let me just write this, because I think it'll simplify my life. Without loss of generality, in some sense, we can assume that m is greater than or equal to n minus 1, else g is disconnected, and the diameter is infinity. OK, so maybe any algorithm can like first check if the graph is connected, which takes order m plus n time. And if it's not, then it outputs infinity. Otherwise, it kind of has like a real problem to worry about. And therefore, we kind of can basically assume m is at least n. And therefore, like instead of having to write order m plus n, we can just write like order m. OK, so this overall time, let's say under this assumption, is order mn. OK? So that's fine. But like this is not like super awesome, right? Because m is at least n. So this is like n squared at least. And if it's a graph that has a lot of edges, like a quadratic number of edges, this is n cubed, which is even worse. But, well, there it is. So that's a very simple algorithm. And I don't know when that was invented. In fact, the more sophisticated version for weighted graphs that uses Dijkstra's was invented in the 50s, because that's when Dijkstra came up with Dijkstra's algorithm. So yeah, you can think that this algorithm is basically 60 years old or something. And in 60 years, nobody has found a faster algorithm than like mn time. Now, people worked on it for a really long time. So this is, a major open question. Faster for 60 years, faster than order mn time for diameter. Okay, so like, the dream here is could you get, order m to the 0.99 n time, or order m times n to the 0.9 time, or better. Which one of these is better? You'd be happier if you got this one, right? Because m is, without loss of generality, bigger than n. So getting a savings of m to the 0.01 is better than getting a savings of n to the 0.01. So like this is like the weakest thing, the weaker thing that you could hope for, right? So like let's not even worry about this. Okay? I mean, let's just even worry about could we possibly get a running time like this, just m times n to the 0.99. Somehow you have to check all the edges for doing anything. So maybe that's your m, but like, do you really have to go over all vertices in some sense? I mean, the BFS already looked at all the vertices somehow. Let me just tell you some facts. Actually, so as we saw last time, if you're stuck on an algorithm's problem, you don't know what to do. One thing you can try to do is an approximation algorithm. I mean, it's better than nothing. And people saw about this. And in fact, there was like a pretty big breakthrough. Well, it's interesting. In '96 by some 4 authors whose names start with these initials. And then it was fixed up, not fixed up, but made like a little bit better by Rodity and Vasilevska in 13. Okay, but the main result is this. They got they got a running time like this, but not for computing the diameter exactly, for approximately computing it. So they got basically up to logs an m times root n time algorithm, which was a factor 2/3 approximation. And let me just tell you what I mean by that. It means that this algorithm finds some number d such that d is between the true diameter and 2/3 of the diameter. Okay, so it doesn't find the exact maximum distance between any two vertices, but it finds some number which is within a factor 2/3 of the maximum distance. Yep?
Tilde on O is hiding the polylog?
Yeah, this means they're actually like polylog n in here. People were pretty happy about that. I mean, it didn't solve the problem, but at least it like had a running time that was better than m times n. Okay, and so what I'll now show you in the rest of the class, which is also from this paper, is that, well, I'll rewrite it on a new board. It's that if you believe this set, then you cannot beat m times n time for a diameter. Okay, so their theorem is that, let's say the CNF-SAT version implies that there is no order m times n to the 1 minus epsilon time diameter algorithm, where this is the number of edges in the graph, and this is the number of vertices. And it's like for all epsilon greater than 0. Okay. You notice I switched to capital M and capital N here. you can guess the reason, right? We're going to build a reduction from SAT to the diameter problem. And SAT has its own m and n, which are going to be little m and little n, the number of clauses and the number of variables. We're going to take a SAT instance and build a graph, which has its own m and n, the number of edges and the vertices. So these will be much bigger, so I'm going to write capital M and capital N for the number of edges and vertices in the graph that we built. Any questions about this statement or what we're going to do for the rest of the class? OK. Well, proof is a reduction. And it's going to be like, it's erased, but kind of like that picture. So we're going to start from a CNF-SAT instance, which is, some phi that's like, whatever, x1 or x10 or x50 bar or x80 and dot, 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 dot. And it's going to have little n variables, x1 through xn, and little m clauses. This is one clause. And don't stress too much about the clauses. It's OK in your head to imagine that it's polynomial in n. It's technically not OK, but it's fine for intuition. OK. And we're going to do a reduction. And this is going to be a mapping reduction. So it's going to be the simplest kind of reduction to a graph G, OK, with n vertices and m edges. And let me just tell you the parameters of the reduction. So this is the reduction part. The time of this reduction is going to basically be 2 to the n over 2. OK, it's 2 to the n over 2 times poly m, actually. Which looks huge, right? Normally we're used to polynomial time reductions. This is like a very slow reduction. It's 2 to the n over 2. But actually, this is totally fine. Because, I mean, we're really going to say that if you have like a fast diameter algorithm, you would get like a slightly fast SAT algorithm. And we just have to, because of Seth, right, our slightly fast Seth algorithm just has to be a little bit better than 2 to the n. So spending 2 to the n over 2 time on the reduction, that's nothing. OK. So how many vertices is it going to have? Basically 2 to the n over 2. OK, let me check my notes. It's going to actually be 2 times 2 to the n over 2 plus m plus 2. OK, but basically 2 to the n over 2 vertices. And m is going to be the number of edges, also basically 2 to the n over 2. It's actually order of little m times 2 to the n over 2. OK, so basically, you have a reduction from an n variable SAT instance. The reduction runs in time 2 to the n over 2. And the graph it makes has about 2 to the n over 2 vertices and about 2 to the n over 2 edges, a bit bigger than that. Yeah, OK. And it's a mapping reduction, so it's going to have the following property. Such that this is what we need to, well, first we'll describe the reduction, and then the main thing will be to prove this. Phi satisfiable implies the diameter of the graph will be 3. And phi unsatisfiable is going to imply that the diameter of the graph is 2. So that's what we're going to prove. And why is that good? Well, let me spell it out. So therefore, once we show this reduction, if you had like an m times n to the 1 minus epsilon time algorithm for exactly computing diameter, okay, which is what we're wondering about. Can you get like m times n to the 0.99 time? Then you could solve, CNF-SAT in time. Well, you'd have to spend the reduction time. So that's 2 to the n over 2 times whatever I say, poly m, plus, okay, so then you need to do order number of edges, which is like 2 to the n over 2, basically, times number of vertices to the 1 minus epsilon. Let me just write. All the dependence on m is going to be polynomials, so let me ignore it. Number of vertices is basically 2 to the n over 2 to the 1 minus epsilon. OK, and so like, what exponent do you have here with n? You have 2 to the half n, and you get 2 to the slightly less than half times n. So, right, so this is all polynomial in m. That hides some big O's. 2 to the 1 minus epsilon over 2n. So for any small epsilon by which you could beat m times n for diameter, for a slightly smaller epsilon, you'd be beating 2 to the n time for CNF-SAT. This contradicts this strong exponential time hypothesis. In other words, if you believe the strong exponential time hypothesis, then this algorithm does not exist. Is the outline clear? Actually, this outline and results is even cooler than I stated. Does anybody see why? Yeah? That's right. It shows that not only could you not have a this time algorithm for exactly computing the diameter, you couldn't even do better than factor 2/3 approximating. Right? Because let's say you had an algorithm that returns you an approximation to the diameter that was strictly better than 2/3. Well, then you could use it to tell the difference between diameter equals 3 and diameter equals 2. And then you would solve SAT. So it's like not only can you not beat m to the n to the 1 minus epsilon for exact computation, you can't even beat factor 2/3 approximation. And that's cool because if you allow yourself factor 2/3 approximation, then you can beat it. You can do it in time n times root n. So it's like a bonus. It's like hardness of approximation even. OK, so we will now do the reduction. And it's easy, although we have 16 minutes. So let's see. OK, so I'm going to describe the reduction. It takes the SAT instance and outputs the graph. And then we'll see all these properties, the running time, and the number of vertices and edges. That'll be clear. And then like the interesting part, which will be not hard, will be to show these two facts. So here's the reduction. I'll just start drawing it. So here's what the graph is going to look like. You're going to have a bunch of vertices for each clause. So I'm just going to name the vertices here, C1, C2, C3, up to Cm. This is m vertices, little m. So the spirit of like these NP completeness reductions, right? And you're also going to have 2 special vertices up here that don't have any name. They're just vertices that hang out. And you connect this vertex to all the clause vertices, and similarly. So you collect as fan out m. This one's also connected to all these clause vertices, m. OK, sorry, this picture is a little hard to see with the racings and everything. So far, it's a very tiny graph, but it's about to get a lot bigger. Here's the main trick that you'll often see in these like reductions from CNF-SAT. You're going to have like a ton of vertices over here. In fact, you're going to have 2 to the little n over 2 exactly vertices here. Okay, I'm going to assume n is even. Don't harass me on that point. Over here. And they're going to be named after like one partial assignment. So you're going to have one vertex for each truth assignment, 0, 1 assignment, to the first n over 2 variables. Okay? So like the name of this vertex is going to be like 0, 0, 0, 0, n over 2 times. The name of this vertex is going to be 0, 0, 0, 1. The name of this vertex is going to be 1, 1, 1. And this you can really think further of like x1 equals 0, x2 equals 0, up to x n over 2 equals 0, and so forth. Okay? I'm going to actually usually call these assignments alpha. So these are partial assignments, assignments to the first half of the variables. And you're going to have exactly the same thing over here, but for the second half of the variables. Okay, so this is another 2 to the n over 2 vertices. And you're going to have 1 for each partial assignment, partial truth assignment, which I'll call beta, to the variables x n over 2 plus 1 through xn. Okay, so these guys will also be named by like length n over 2 strings. This one corresponds to x n over 2 plus 1 equals 1, up to x n equals 1, and so forth. Okay. Still haven't finished drawing the graph, but I've actually finished drawing all the vertices. So there's 2 times 2 to the n over 2 plus m plus 2 vertices, which I think is what I promised. And there are going to be some edges between these vertices and these vertices. Okay? But let me come back to that. Some edges, which I'll define in a second. And similarly here, there's going to be some edges from these vertices to these vertices. And let me just say that I'll define them later, but there's going to be at least one edge for all alpha. Every vertex here is going to have at least one edge up to here. I'm just going to promise you that. I'll tell you what they are exactly in a second. And similarly here, at least one for all beta. Okay, so I want you to think about the diameter of the graph so far. Now, while you're thinking about that, let me collect up a few other things so far. Okay, so far, I haven't told you how to put in these final edges, but it's not going to be very complicated. So the time so far of the reduction is, I don't know, roughly 2 to the n over 2. I mean, basically, it's got to like plunk down all these vertices and plunk down all those vertices. I mean, write their names. It's going to plunk down the m. So like, I don't know, maybe order m. I mean, it's got to do the m stuff. Let me just say poly m times 2 to the n over 2. Okay, and this is also going to be the time for filling in these edges. I mean, there's only m times 2 to the n over 2 possible edges here, and we're going to put in a subset of them. And the number of vertices and the number of edges and an m are basically as I claimed. I mean, no matter how I fill in these edges, as I said, there's going to be at most m times 2 to the n over 2 of them. Same over here. So that's what I claimed about the number of edges. OK, now let's think about the diameter so far. Well, what is an upper bound of the diameter so far? It's at most 3. I mean, no matter how we put in these edges, as long as this is true, the diameter is going to be at most 3. So why is that? Well, you kind of just like imagine you have to find the farthest apart pair. So I mean, I don't know, this vertex, it can get anywhere in at most 3 hops, right? It can get here in 1, it can get up there in 2. Let's say if you're just within the top part, you can definitely get everywhere in 3 steps in the top part. In fact, in 2 steps, from there to there to there. Or if you want to go from one clause to another clause, you can go up to one of these and back down. So in the top part, the diameter is 2. Now suppose you have a pair of vertices, one of which is down here in the vertex stuff. Well, it's still OK. Because of, like, let's say you're starting from this vertex. Because of this promise, there's at least one edge up here. And now you can get anywhere else in 2 more. Is that true? 1, 2, 3. Ah, no, it looks bad. Can you get from here to here in 3? No. OK, so then in my notes, I thought you didn't need this, but I guess you need this. Let's put a clique here. OK, so let's put all possible edges in here. And now you can definitely get from anybody here to anybody here in 3. You can go up. There's going to be at least one edge for every vertex down here, and at least one edge from any vertex here up into here. And now I put in all possible edges here. So this distance at least 3. OK, so actually, I guess, well, I'll put a square here. It doesn't really matter. It's more like plus order m squared rather than times order m squared. But anyway, it's true. OK, putting in all the little m squared edges here doesn't make much difference. OK, well, I'm a little slightly nervous now because I changed my construction a little bit. But I think it's OK, right? So far, so good. The diameter is at most 3. OK, so the diameter is at most 3. That's good. And now we just sort of need to think about under what circumstances would the diameter become 2? I mean, it's going to depend on what edges we put in here. Right? So like all the edges up, all the vertices up here, they can get between each other in 2 steps. And from a guy down here, it can get into the clique in 1 step. It can get to these 2 special guys in 2 steps. So whether or not the diameter is 2 is all about whether you can get from every guy over here to every other guy over here in at most 2 steps. Right? Whether or not the diameter is 2 depends on if for every vertex over here and every vertex over here, there's a length 2 path. And that's going to happen. I mean, the only way there can be a length 2 path is if you go like right up to a clause and come right back down to the appropriate vertex over here. OK, so let me write that. OK, it will be 2 if and only if, basically for all alpha on the left and beta on the right, there exists some path that looks like this. Alpha goes up to one particular clause, Ci, and there's also the edge down to beta. OK. So now I'm going to tell you how to put in those edges. So here it is. So we're going to connect alpha to Ci. OK, use the same notation here, but I just mean for any alpha and any Ci, I'll put in an edge if and only if Ci is not satisfied by alpha. OK, if it's not already satisfied by alpha. So for example, like let's say Ci is x1 or x2 or xn. And alpha is the vertex that's like 0, 0, 0, 0 up to 0. This is x1. This is xn over 2. Here, I would put an edge. Because if you plug in all zeros for the first n over 2 variables, you have not satisfied this. Actually, one of the variables is still free. But like in particular, you haven't satisfied this. On the other hand, this vertex, 1, 0, 0, 0, you would not have an edge. Because this partial assignment sets x1 to 1. And so it's already satisfied this. OK? And it's same for betas. OK? So for example, the beta vertex, which is like 0, 0, you would have an edge, because if you plug in zeros for all the last n over 2 variables, you don't satisfy this. But the one that ends in 1, there'd be no edge, because this one has xn setting to 1, which does satisfy this. Any question? OK, at this stage, there's a tiny twist. The proof is almost simple, except for a tiny twist, which is that I told you, I promised you that every vertex up here would have at least one edge up here. And that's not quite true. Like, if you have some alpha, if that partial assignment alpha satisfies every clause, then you don't put any edges from it. But that's actually a really easy case. If that partial assignment alpha satisfies every clause, then it satisfies, it doesn't matter, you set the other variables, it satisfies the clause. So at this stage in your reduction, if you're putting in these edges and you're like, holy cow, there's no edge from this particular alpha to any clause, you're like, it's satisfiable. So what do you do? Just if some alpha has no edges, it's going to be the same for beta. You know phi is satisfiable. So you just abandon everything, and you can output this graph. Just output any graph of diameter 3, right? Because that's what you're supposed to do. OK, and similarly, if there's some beta that has no edges. OK, so as you're doing this reduction, there's some rare cases where you already know the answer, it's satisfiable, and then you can just trivially output something with diameter 3. OK, so we're going to henceforth assume that doesn't happen. And so now this little promise is satisfied. Same for the betas. OK, so we're basically done. So that's the final definition of the reduction. It has the right time and number of vertices and everything. And now we just have to check this. That when you make the graph this way, if it's unsatisfiable, you'll get diameter 2. And if it's satisfiable, you'll get diameter 3. We know that the diameter is always going to be at most 3. So we really just kind of have to check that it's satisfiable if and only if the diameter stays 3 after putting in these edges. OK, so here's the claim. This is going to be the keyboard. So let's say you have a pair, alpha and beta, a vertex over here and a vertex here. They have distance 3. Even after you put in the edges, if for all ci, we don't have both edges like this. OK, two particular alpha and beta are at distance 3. If there's no clause vertex, you can go up and down to. OK? And what does this mean? This, by definition, is if and only if either alpha or beta satisfies ci. That's the definition of when you, if you have both of these things, it means they both don't satisfy it. Right? So if you're missing one of these edges, then it must be that either alpha satisfies it if you're missing this edge, or that beta satisfies it if you're missing this edge. OK. And this is if and only if the combined assignment, sorry, this thing now, assignment alpha together with beta satisfies ci. Actually, sorry, this thing. Right? If a full assignment to all n variables satisfies a particular clause, then at least one of the literals in it is made true. And that literal is either in the first half of the variables or the second half of the variables, which means that either the partial assignment alpha to the first half of the variable satisfies it, or the partial assignment beta to the second half of the variable satisfies it. So you can think of alpha and beta, a pair of vertices, as a pair of vertices or as like a full truth assignment. OK, and now you see that like this whole thing, for all clauses, the combined assignment satisfies them. This is equivalent to the combined assignment alpha plus beta satisfies phi. Yep?
The alpha that doesn't satisfy C, there should be an alpha that doesn't satisfy all C sub I, right? One satisfying assignment.
So what I'm saying is alpha and beta have difference 3 if for every clause you don't have both edges. Now fix one clause for a second. To say that you don't have both edges, by definition, is to say that either alpha or beta satisfies it. And that's the same as saying that the combined assignment satisfies it. Like sticking them together satisfies it.
Yeah.
Because on one hand, if either of them satisfies CI, then certainly the combined one does. And on the other hand, if the combined one does, then like it's satisfied because of some literal, which is either in the first half or the second half. Or both, but that's OK. OK, and then to say that this happens for all clauses, CI, is to say that the combined assignment satisfies the whole CNF.
You know that alpha, beta are the same for each clause.
We're fixing alpha and beta here.
Oh.
Sorry, like, yeah. So first, fix alpha and beta. And then to say that as vertices they have distance 3 is ultimately to say that as combined partial assignments they satisfy phi. So yeah. So in other words, phi is satisfiable if and only if there exists alpha and beta at distance 3. Which is if and only if the diameter of the graph is is 3. So the existence of a satisfying assignment for phi, if you split it up into alpha and beta, gives you a pair of vertices on the left and the right that have distance 3. There's no clause that they can both jump up to make a distance 2 path. That's the end. Sorry for going over time. Yeah?
So what does Contrapositive algorithm do when you run about this graph?
I guess a